Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside as we jump into the section 6.1, 6.2 quiz in the Big Ideas Math Integrated Math 3 textbook. This is just on inverse variation and graphing rational functions. Now, inverse variation doesn't have very much to it. Graphing rational functions kind of had a lot to it, depending on the kinds of questions they asked. And really just where they went from there. But we have 13 questions in total from here. Looks like a good balance of both. I didn't really get to see the questions as a whole, but 1 through 7 looks like they're off inverse variation, so maybe all the rest after that are graphing. I'm going to attach graph paper down below in the description section with the PDF, as well as the single page that we do have on the 1 through 13. Should be a pretty quick video overall. Check out the timestamp for the problems down below as well. Without further ado, I'm going to go ahead and get started. We are looking at numbers 1, 2, and 3, where they ask tell whether x and y show direct inverse variation or neither, and explain your reasoning. This is really all about whether you have a constant flow of something. Now, let me just write these up top. Direct variation is a setup where you have y equals a times x, where a is the constant, and if you divided both sides by x, you'd get a equals y over x. So basically, when you divide your two variables, you get a constant out in direct variation. And inverse variation is an initial setup where it's y equals a divided by some x, and when a is by itself, multiplying both sides by x, you get a product of your two variables as your constant. So do you have that basically, or can you get it in those forms, are the two questions that we're kind of asking within. So on number 1, we have x plus y equals 7. When I get y by itself by subtracting x over, it's linear, but it ain't direct variation. This isn't the same thing. It's not just having a slope, means that it's also not having a constant. When x equals 0, does y equal 0? The answer is no. This is a case of neither. I'm not getting too deep into the whole why it's not in terms of writing, but I am going to state them out loud. But basically, if I can get them in those forms. Number 2 says 2/5 x equals y. Isn't that just another way of saying y equals 2/5 x? I do believe so. So as we get, maybe we should include that x. So as we get a rewrite where it says y equals 2/5 x, this is indeed in the form y equals a times x. This is a direct variation setup where a, your constant variation, is 2/5. So this is direct variation. It is in that form. Direction. Direction is a hybrid of direct and variation. There we go. Direct V. Okay, number 3. X times y equals 0.45. Now this in and of itself would actually be fine to leave it like that and state what it is. It's actually not direct variation when the variables multiply. It's actually inverse variation. See, when I divide both sides by x, here's what I'm going to do the alternative of. When I divide both sides by x, I get that y equals a over x setup, which is how inverse variation works. So this is inverse variation given that we are in that form. Now, the next 3 are a part of the same question set. I shall copy and paste these tables over. It says tell whether x and y show direct inverse variation or neither. These ones are better off to look at the division to see if you get a constant, or multiplication to see if you get a constant. So when y divides by x, you get a constant on a, or when x multiplies with y, you get a constant on a. That is what we're seeing, or that's what we're seeking on these 3 here. So on number 4, I apologize for them being a little blurry. What I do want to check out right now is as x gets bigger, y gets bigger. Therefore, there's no way that this is inverse variation. If anything, it could be direct variation. So I want to check y over x. Forget x times y. That will not be a constant. But y over x, let's see. 9 divided by 3, 18 divided by 6, 27 divided by 9, and 36 divided by 12 are all constant. Because you have a constant y over x equals 3, this is an example of direct variation. See, if I did a rewrite of this, it would be y equals 3x, right? Y equals 3x. Not that they're asking us to write that, but that's what we can do. We're probably going to be asked to do something like that later. Y varies directly with x, and x is 6 when y is 18, or whatever. Y is 18 when x is 6. Write the constant, come up with the equation, yada, yada. It's that kind of thing. So there's direct variation number 4. Excuse me, number 5. On number 5, a little cut off there. As x increases, well, y, it's decreasing on the negative side. So, it might be increasing, like getting more positive, but it's decreasing on the negative side. They're smaller numbers. So when we look at products, that's what we care about. I'm going to check and see if the products are constant here. There's no way it can be direct variation. There's a way it could be inverse variation. 1 times negative 24. 2 times negative 12, 3 times negative 8, and 4 times negative 6. If any one of these breaks, then it ain't constant. But as long as all of them are the same, we're good. Because the product is constant, this is an example of inverse variation. I'm not going to get into the whole equation on this one. We'll do that when a question asks us, and I'm sure one will. Number 6, maybe a neither. We'll see. Number 6, as x increases, y decreases. That's only possible through inverse variation. And remember, the section was actually on inverse variation, so it wouldn't surprise me actually if this was inverse variation. Let's try another x times y again and see how that pans out. But if it ends up being not constant even once, then, we break. 2 times 72. 36 times 4, I think, is also 144. 6 times 18 is not. That's 108, right? Oh, no, what is that? 108? 108, and 8 times 9 is 72. It only took this break to say, nah, that ain't it, or that as well. Just because 2 of them multiply to become 144 doesn't mean all of them do. This is a neither case. It was good for a moment, and then it cut itself off. Number 7 says, and this is the kind of thing that I was stating where we actually write an equation based off of it. So the variables x and y vary inversely. So we do know that our setup can already become y equals some sort of a over x. Given that, it says y equals 10 when x equals 5. So y equals 10 when x equals 5. Let's find the constant of variation that makes this so by multiplying both sides by 5. You get an a value of 5 times 10, which is 50. So our equation, they say write an equation that relates x and y equals 50 over x. This is our inverse variation equation. It says then find y when x equals negative 2. It's a straight substitution here, 50 over negative 2. I've mentioned this previously, and I'm going to mention it again right now. Inverse variation may fit in this chapter for rational functions because, by and large, this is a rational function. Heck, we can graph it. Not that I'm going to, but, we can graph this thing. This isn't really the rational stuff that we're, playing with. The direct variation you learned in apparently 7th grade math. So inverse variation, this could be part of 7th grade math stuff, what we just did in this problem. Very straightforward, but this belongs with rational equations, and that's what we're doing. Speaking of which, let's start doing some graphs. Numbers 8, 9, and 10, they say match the function with its graph, explain your reasoning. This is almost a set where I feel like I almost want to do some copy-paste of these graphs. Let's see. Give me one moment. I'm going to find the high-quality versions of these graphs and just get them ready to go. So graph A, I'm bringing on over. I don't know if number 8 is graph A, but I'm getting high-quality versions of them. Hope you all don't mind. So graph A, putting it on the side. I'll get it ready when I need it. Graph B. We can probably point to them from the small ones, and then I'll bring it over and say, see, it's going to be this one. So graph B, bringing that one over. Pardon the hiding of it for a moment. And then graph C. Sorry about this. Did not prepare for these questions. I don't look at the questions beforehand, so I just saw there were a bunch of inverse variation questions to begin with. And graph C over on this other side. Okay, so let's look at number 8. Now listen, we could graph these on our own. I think they're going to have us graph some later, I'm sure. But we could graph these on our own as well. So number 8 is f of x equals 3 over x plus 2. Now, if I were to come up with the information on this graph, here's what I'm looking at. I got an a value of 3. We'll talk about how that works in a moment. But let's start with asymptotes. I got a vertical asymptote at x equals 0, the equation of the value of x that you can't plug in because we can't divide by 0. So there's a vertical asymptote there. There are no values that exist there. Horizontal asymptote is going to be at y equals 2. It's basically this k value. There's a shift of that. If this 2 wasn't here, it would be at y equals 0 because I couldn't plug in a value of x and get 0 for y. It'd be impossible. Now I can't plug a value in for x and get 2 for y because a non-zero number plus 2 is a non-2 value. So I'm going to look for a vertical asymptote of 0 and a horizontal asymptote at 2. I'll begin with that and see if there's anything else I want to play with. It looks like graph C does exactly that. Now we'll talk about the rest of the graph given that. Just by its nature, it looks like here's a vertical asymptote and a horizontal asymptote like that. The 3, what I've been doing with the graphs is if you start with this as like your origin, divide 3 by 1 and you get 3. Divide 3 by 3 and you get 1, things like that. 3 divided by 2 is 3 divided by 2 is 1.5. 3 divided by 1.5 is 2. Those are other nice points. So that does match what this is. 3 over negative 1 is negative 3, etc. So this seems to follow exactly what we were talking about. Divided by 2 is 1.5. Divided by 1, negative 1.5 is negative 2. So this is graph C. That's my reasoning behind what I'm doing there. Let me get graphs B and A ready as I move on to the next page. But we do have number 9 next. So that was C, right? C gone. Number 9. Pasting this over because I need them later. Let's get them. Number 9, we have y equals negative 2 over x plus 3 and then minus 2. Once again, if I go from asymptotes alone, I think this will resolve what we're talking about. This is x equals negative 3 as a vertical. That's what we plug in to get 0, which would be a problem. That's why there's an asymptote there. Horizontal asymptotes at y equals negative 2. Now, the one with the negative 3, negative 2 looks to be a. So I'm going to bring that in the fold. And let's talk about how the negative 2 right here for the actual a comes into fold after that. So x equals negative 3. Y equals negative 2. And then the negative, you can tell the negative flips this thing over, but it's more about just, negative 2 divided by 1 is negative 2. Negative 2 divided by 2 is, negative 1. Like that. Negative 2 divided by negative 1 is positive 2, and then a positive 1 here when you divide by negative 2. So, that seems to fit exactly what we're doing there, and I'll just finish off that. So number 10 must be B. Let's see if we can find all the connections that make that so. But on number 10, we originally have y equals 2x plus 2 over 3x plus 1. Now, a couple things you can do with this. For one, my vertical asymptote is where I set this bottom equal to 0. If I subtract 3, or if I subtract 1 and divide by 3, you get x equals negative 1/3. That is the equation of this asymptote. It's a fraction, but it's there. Horizontal asymptote is discovered by dividing the two coefficients of your highest degree term if they're equal. These are both x to the first power. We can divide 2 by 3. We get y equals 2/3. Strange fraction asymptotes that we have, but they are the asymptotes. And graph B looks to resemble that. Here's y equals 2/3, literally. That's a fraction. These are not scaled wrong. This is literally it. And x equals negative 1/3 looks to be the vertical asymptote of that one. So they really seem to be exactly those ones. There's no a value that we see here because this isn't divided in any such way. But if I can show you other critical points that would work out, it would be these. An x-intercept you can find your x-intercept by setting the numerator equal to 0. You have to find out for what value of x gets you a 0 on top. So it gets you 0 for y. So when 2x plus 2 equals 0, subtract 2 divided by 2, you get x is negative 1. And that is a point that's on this graph right there. And then the y-intercept, you set x equal to 0. And in setting x equal to 0, take h of 0. 2 times 0 plus 2, 3 times 0 plus 1. You get 2 over 1, which is 2. So 2 is this guy right here. So everything seems to be matching from what we have. It's not every point under the sun that we'd get. I could do the division version of this thing, but honestly, because these are already fraction asymptotes, I don't think there's any real value in doing that. We found points that confirm this is what it is. Good to go. By process of elimination, we should already know that 10 was B. Number 11. Okay, number 11 is an example of rewriting something in the form. Let's see if these are actually pretty clean numbers. I'd like for them to be. So this time we're going to take something that is of this original appearance. Whether or not you choose to do the graph on this is going to be up to you. But because they're forcing us, they say write it in this graphable form. We can do that by using long or synthetic division. Now the book made a point of using long division, and it's not long. We do it once. X goes into 2x twice. You distribute the x plus 8 into 2, so you get 2x plus 16, and you subtract this result, you get negative 7. So the quotient is, if we do a rewrite of this thing, the quotient is the guy without a fraction involved. I'm going to write that actually on the outside here. Excuse me. That is the remainder. The quotient is 2, and the remainder is negative 7. The remainder is the thing that is still dividing by, well, here's something, your x plus 8. So this is the form rewritten, whether I used long or synthetic division. This time I used long. Plus 2, plus 2. And now we can graph out of the form as we did before. They said describe the graph of G as a transformation of the graph of f of x equals a over x, as if the f of x equation would be negative 7 over x. Still the same a as you're seeing right there. What we're seeing is just a change in translation, but let's get the entire graph done based off what we see here. Now based off, oops, I still have those. Let's get graph paper. There we go. Or graph axes. We might only have to do one graph though, so sorry if you do a printout for just one single problem. So the x plus 8 means you have an x, a vertical asymptote at negative 8. Not really ideal for what we kind of want to do getting on both sides of the graph, but that's the problem. And y equals 2 is our horizontal asymptote. Negative 7 is that a value. That means I can divide negative 7 from here by 1 to get negative 7. 7 down from there. Divide by 2 to get, well, negative 3.5, let's put it. Let's divide by -3.5, or by 3.5 to get 2 as well. Why not? And then divide by 7. 7 from 8 is right here, to get 1. Well, -1. And I can divide by 14 to get 1/2. I did a lot of those earlier on, so 14 over is at x equals 6, and you get a 1/2. And I can divide by 1/2 to get 14, but 14 down from here is a little off the grid. I'm still kind of getting the idea of it. So there's a curve I can get for this rational function here. If you did a lot with me before, then you understand it. I even linked some videos of some other basic and complicated graphs that you can do. So hopefully you get a great idea of what I'm doing. Here's the thing. You can use a table. You can use a table, but I'd rather know what x values I'd like to plug in, which is how far away from the vertical asymptote I like to go, by choosing numbers that I can easily divide by 7. I don't want to randomly plug in x equals 3 and find out that that number is 11 away from 7, and -7 over 11 is the... We'll have to do -7 11 plus 2 and then work off that. You know, there's no fun in that. There's no fun in that. So I'm not really using a table of sorts, but I am still getting exact points. -7 over -1 is +7. 7 up from 2 is 9. And that's really all I can fit. Let's do the divide by 2. You get 3.5, so 3.5 up from there. So there's another feature of the graph that's going over here. And compared to the f of x graph that we would have had, which was just -7 over x, this is translated 8 units left and 2 units up. So that's what we can say for this number 11. So the graph of G is a translation 8 units left and 2 units up from F. Now, we did not graph this using what we did on number 10, just kind of talking about intercepts and things like that. But let's confirm everything is as we expected it to be, even on this graph from there. If I did the vertical asymptote would be the same thing, -8 based off this. Horizontal asymptote, I'd divide 2 by 1, the coefficient here, and I'd get y equals 2. That's exactly what we had. The x-intercept, although we never plotted it ourselves, well, we did actually. The x-intercept, we set 2x plus 9 equal to 0. If you subtract 9 and divide by 2, you get x equals -9 over 2. -9 over 2 is -4.5. Do we have an x-intercept of -4.5? You betcha, it's right there. The y-intercept is when you set x equal to 0. These go away. You get 9 over 8. Do I have a y-intercept of 9 over 8? Probably. It's this one right here. 9 over 8 is 1 and an eighth. This is 1y is 1, so this is a little bit above it. So that makes a bunch of sense. So those are the points we'd get on top of what we got from those asymptote ideas. And using division really helped us identify it based off that a value being -7. All right, we have 2 more questions to go. Number 12 says the time t in minutes required to empty a tank varies inversely with the pumping rate in gallons per minute. Hold on. The time it takes to empty a tank. Okay, so this isn't about filling up a tank, it's about emptying a tank. So the faster that you have a pumping rate, the less time it takes. The rate of a certain pump is 70 gallons per minute. It takes the pump 20 minutes to empty the tank. So for that speed, we can come up with a constant of variation. So we have some sort of y equals a over x. Actually, forget that. Let me just write down the numbers. Y looks like is the time. Actually, time varies inversely with rate. I'm going to do it like that. All right, so it takes the pump 20 minutes at a rate of 70 gallons per minute. So we can now find out A as 1,400. If you multiply 70 with 20, you get 1,400 minute gallons. No, gallons. I always say those wrong. Gallons, what do you just multiply those? 1,400 gallons as a total thing, right? So that's the constant of variation, is it's always 1,400 gallons to empty. Now, with these rates, what are the certain times that we have? So T equals 1,400 over R is basically what we're dealing with here. That's our equation. It says complete the table for the times it takes to pump the tank with the given rate. So now we got to divide 1,400 by 50, 60, 65, and 75. And I don't believe all of these numbers are very beautiful, so I'm going to use the calculator here. 1,400 over 50. That should be beautiful. It's exactly 28. That is very beautiful. Excuse me. It takes 28 minutes there. 1,400 over 60 is also 14 over 6. No, it's not. It's 140 over 6. And that's it's 23.3 repeating. So I'll say 23.3 minutes. And you can see as the rate goes up, the time goes down. That's how varied inversely stuff works. So 1400 divided by 65 is about 21.5. Not exactly, but it's around 21.5. And then 1400 divided by 75 should be smaller. And it's around 18.6 repeating, or 18.6 repeating, so I'm just right, 18.7. Now, remember, 70 got us 20 minutes, and 20 fits, 70 is wedged in between 65 and 75, and 20 is wedged somewhere between 18.7 and 21.5. So I believe my answers, they're looking good, and they didn't ask any other questions. Sometimes they say, you know, what happens to the time as the pumping rate increases, which you'd say that the time goes down. All right, we got one more question to go, guys. It is number 13. On number 13, it says a pitcher throws 16 strikes in the first 38 pitches. The table shows how a pitcher's strike percentage, that's not good. That's low. Normally you'd want to be around 62% is seems to be an average when all said and done. I really have felt that. 2/3 is great. That's low. That's low. Anyway, the table shows how a pitcher's strike percentage changes when the pitcher throws X consecutive strikes after the first 38 pitches. What? Write a rational function for the strike percentage in terms of X. Graph the function. How many consecutive strikes must the pitcher throw to reach? Oh, I see. How many they must throw in order to reach certain percentages. I thought they meant like if they go on a strike throwing streak, randomly throughout their set. I'm like, what's going on? That's not how that works. Okay. Anyway, so we have a table. Let me just copy and paste it over so we can see the numbers a little bigger. If you're watching on your phone, you might not even see what these numbers are right now. So let's get to here. Okay. So there are some numbers. Great. Now, total strikes over total pitches gets you a strike percentage, right? You divide 16 by 38, you get this number. 21 divided by that, you get this number. This divided by that, etc. So X plus 16 over X plus 38, and you get a strike percentage of X plus 16 over X plus 38. Now, X is a value that we have to find out so we can get a strike percentage of 60%. So we have an equation. It could say, I'll do f of x equals, but, y equals X plus 16 over X plus 38. And they said, graph the function. Now, I'm going to use the graphing calculator. I hope that's okay. We have a vertical asymptote at negative 38, and honestly, that doesn't even apply. X has to be, 0 or more. It's the pitches after 38 pitches. So anyway, let me go to the graphing calculator here. We're going to plot in X plus 16 over X plus 38. And, I just want to rehash here what kind of thing we're looking for. We only care about number of pitches after. Let's go like 50 or something like that. And a percentage, this is a percentage. It just goes from 0 to 1, right? Something to 100%. So let's look at this and see where our graph is. So it's going that way. And what it's showing, remember, there's an asymptote that's doing something. We're not seeing the asymptotes. This is just a portion of the graph where we can see some good stuff. And I think it is good stuff right here. We have to find out where we reach 60% given this graph. Now, this is a really zoomed in graph. We're only really looking at, again, values that we care about. I'm going from 0 to 50, I believe, 50 pitches later. And this is 0% to 100%. This is strikes thrown. Because we are increasing our number of consecutive strikes thrown right here, your percentage is increasing. But the percentage has to flatten out a little bit. You never actually truly get 100%, right? You were already 22 pitches less than that total. You can only approach it more and more as time goes on. And you can approach it. You can throw a billion pitches. You'll get it 99.9%, whatever, but never actually be 100. Anyway, we got to figure out what value is like that 60%. And I'm not saying that's 60, but we're trying to figure out, like, boom, like if I projected, I'd say, oh, that's around 15 pitches or something like that. I don't know. We're going to come up with this by looking at, shoot, I made that up. I don't want you to write that. We have to come up with what X value it is so that f of X is 0.6. F of X is 0.6. So we go back to the graphing calculator. We can use the trace feature here, and we can find 0.6. Say best one's around there. It's around 17 pitches, honestly. So X is around 17. So for f of X equals 0.6, X is around 17 pitches. Now, is that exact? I have no idea. What we could do is double check algebraically, which is one way to go about it. 0.6 equals x plus 16 over x plus, sorry, not pitches, but strikes. That many consecutive strikes, right? But it is consecutive strikes, so it is pitches as well. Let's try that. X plus 38. Let's multiply. I don't really like the decimal, but let's multiply both sides by x plus 38. You get 0.6x plus, and this is kind of overkill on this part of the problem because I think I got it right. So 38 times 0.6, we get 22.8 equals x plus 16. If we subtract 0.6x, we get 0.4x. If we subtract 16, we get 6.8. Divide by, yeah, that is. Divide by 0.4, that's x equals 17. So 17 strikes gets you a 60%. And that's what you need to climb up to. That's a lot. Throwing 17 strikes in a row is a lot, which just goes to show how low their strike percentage truly was when you think about it from before. So sorry that I didn't get the graph in full here, guys. It would be something where you'd have a y. You'd have a vertical asymptote at negative 38, but it really doesn't apply to whatever we're doing. And then you have a horizontal asymptote at 1, and that totally applies because our graph, when it does something like this, this is the part that we care about from here onward, because these are the pitches for x after throwing the first 38 pitches, right? After the first 38 pitches. So we look at that. So that's it, and that's all, guys. That'll do it for this one. This is Mr. Robinson. Thank you so much for watching. And after this, we do a lot more algebra in simplifying rational expressions and solving rational equations. So hold on to your butts for these ones, guys. It's going to be a doozy. Take care. Thank you so much. I'm going to see you in the next one.